Okay, so then I did the yellow, and I got the enters and exits of the loops at 30 and 150. And you draw not just 30 and 150, you draw the yellow all the way through. Okay, then next comment, Izzy made a comment. She goes, hey, the only place it's blue is between 30 and 150. Correct. So I took the sticks that I drew between 30 and 150, and I put them in there back on the loop between 30 and 150. And the stick length on the left is the stick length on the right, and it goes from little blues up to the teal, and then the teal back down to the smiley face. Do you see the symmetry there? Okay, the part that bugs us is the reds. So the reds, like the very first moment, I really want to be in this piece right here. Do you agree the first 30 degrees, or if you want to call it the first 30 seconds, you really want to be there, but where are you? Backwards on the other side because of the negative radiuses. It bugs you, but this is actually here. So I'm actually going to get activated there first. That's my first region. What's my next region of coloring? Are you okay? It's here, and it's what I want it to be. Why do I want it to be there? That's my next region because that's between 30 and 90. And actually, couldn't I color this all the way in? Because between 30 and 150 do I get what I get. Now, where's the next zone if you run the clock backwards in time? Where do you really want to be? You really wish you could be here, but what's going to happen over there? They're negative radiuses, so I'm not in that puzzle piece. Where does that puzzle piece go? Flip it and move it. Good with that? Then, where do I want to be next if you run the clock? The key thing is you got to run the clock. If you run the clock next, we'll go here. I should be here. But what happens? It's negative again. So I'm over here. You guys good with that? And then the next piece should be a humongous one. The next one should be a humongous piece here. Should be all here. But what happens again? That whole zone, like zoning houses or something, that whole zone should be there, but what happens? It gets flipped up to that zone. You guys okay with that? Now I have one zone left. Where is it that it should be? Between 330 and 360. My last zone of the day should be here between 330 and 360. It should be there, but again, what happened? It's negative, so it's on the opposite side of the world. And probably if you just stare at the map there, you're like, wow, Bach, that didn't actually help. That made it worse. But let me show you the drawing now. Here comes the drawing of this. Now what? You guys okay with that? And I have it. Now, showing it to you. That is it there, but I can animate it for you, which you might like better. The animation of it. Here we go. Oh, da, da, da. Here we go. Like that. Okay. Now, it should not take us that long always to do these. Okay, these are special guys. They're called limicones. I'm going to kind of organize the limicone for you in a second. But is that getting sort of better? Your ideal on any clock. Let's say I go through it. Let's say my poles are here and here. And I'm going to tell you all the radiuses are positive. How do I activate each section here? What's the first section I would draw? Next. 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 And that's what you got. So it would look something like this in live time. Maybe, but I'm not negative, so what would I do? Woohoo! Not negative, so then I go back out. Not negative, so then I go back out. Not negative, so then I go back out and I draw a 4-leaf clover like that. And that would be, if I was showing you my metaphor with the blues and reds, there would be no reds. All of it would have stayed blue. You would love that. You guys good with that one? So then the question would be, if I drew it again, and I go start positive, flip signs of radii each time. So I'll say you start here. Okay? If I start there positive, what's going to happen? What's first zone? Okay? Then what? So I'll draw that. Next zone. Down. It's the down zone because I went in the negative world of what I wish was up top. And so then it would be a loop like this to there. Now what? Now it goes back green because it's what I want it to be, and it is that. So then I go green. Now I'm finishing up. I'm already at like 230 to like 300. I'm already in like the third and fourth quadrant in my brain, but what are the radiuses turning into? Negative radiuses. So then I'm coming backwards in time to here. And then, if you want, you can call this like section 5, which is really the beginning of section 1, which gets me that. Okay? So then that would have drawn like this. I got what I wanted. I should go into the top loop, except I just got negatized. I should go into left loop, and I do go into the left loop because I get what I get. Now I should be down south, but it's backwards in time. And finally, I'm coming into where I should be. You guys okay with that? Anyone work on their project already? And let's say, specifically, let me draw a nice circle here. We'll go with this circle here. And let's say that was what the whole thing was in. Okay? And it's not. Sorry. Let's say that whole circle had a radius of 8. Can anyone tell me what this graph is? 8. Not sine. Cosine. 2 theta. Correct. 2 theta. 2's even, so you actually get 4 petals. Evens, you double. Good hint. Second thing, the reason it wasn't sine and it was cosine, where was the first petal? Directly out on the axis, directly due east. If I rotated this 4-leaf clover a little bit, like up to, I don't know, 45 degrees, if I rotated it a little bit where the clover started more like that, it would have been sine. Now the beauty of a video versus what I just drew is that accurately drawing sine if I did 8 sine of 2 theta. Again, in live time, this is how I drew it. Let's go. I'll highlight what I did. Is that the correct drawing of sine? No, because what's going to happen with radiuses when you do the sine, just like you do the cosine, it gets you what? Well, you get some negatives. So that guy would have drawn something more like this. All right, let's try that again. I forgot to connect it. Good. Now where? Down and right. Then, yes, I got what I wanted, and then now I'm backwards in time. Okay. Again, a PDF of this file looks like we did nothing, but a live video of this file is amazing. So you're very welcome, Rowan. Hope all's going well. All right. So next thing is this. You can write things down if you want. I'm going to hit pause. No, I won't. I'll keep talking. Parametric and polar. There's a lot of formulas out there. There's a lot of kind of go-to problems that are what I call plug and chug. Then there's going to be a lot of problems that are harder, which are think and link. Plug and chug, I give you a formula, you can go get it. What's a speed formula? Oh, what's dy dx? Oh, that's dy dt over dx dt. The ones that are harder are the think and link, like what we just did. How do I draw this picture? How do I represent this picture? So half of the test is like, here's the easy formula, plug and chug. You love plug and chugs. Let's look at the parametric. What stuff would you say is plug and chug on the parametrics? Dy dx, love it. Speed, arc length, everything. Maybe in the red. Now maybe some of you don't like the projectile part in the red. That could be a little bit of a think and link, because what you're linking is, okay, there's an X movement, which is middle school math, and then there's a Y movement, which is free falling calc 1. And you might say that's a think and link because there's two types of movement at once. Fair enough. Okay, but do you agree a lot of the parametric, there's formulas, you plug and chug, and you do it. What makes it hard on the AP test is how good are you at your calculator. That's really what they're testing is, do you know how to do second calculate intersect, second calculate zero, second calculate integral. It's all of the calculator stuff is what they're checking on you. They know you know the formulas, just can you follow through with the formulas. Now let's look at the polar. How about dy dx in polar? Does it look the same as dy dx in parametric, but instead of t's it's thetas? That's not bad. We're not going to do arc length, so don't worry about the arc length part. Okay. Polar, maybe a lot of the conversions in polar for you are still think and link. Even though it's a formula, the polar conversion is all based off of x, y, theta, and r, but maybe for you, you're still thinking and linking on that, okay? But can you kind of see there is a lot of formulas out there that aren't trying to be hard. It's just when I make you draw something or when I make you interpret something, okay? So here, these are some of the special graphs, okay? You're doing a whole project on 3. Do you guys agree? That's really what your project is on, okay? And the one I just did with you for 20 minutes was number 4, the Limicon. And I want to talk about the Limicon in a second. Luke, what's up? Area. That's our whole lecture today. So you don't worry about writing it yet. That's my whole lecture today. So the Limicon guys, like the one here, okay? We worked through that and we did a lot of details. Do you agree? Okay? A way that you should at least recognize it is this. Okay. Plot 4 points for me now. Plug in 0. What do I get? -3. Okay. Plot 90. What do I get? Okay. Plot 180. What do I get? Plot 270. What do I get? Okay, notice I plotted those a little bit. Okay, and then plot 0 or 360. What do I get? -3, which is back to here. Okay, and then you just go, oh, it's one of these loopy things that maybe you kind of draw it like this first. I drew it. What should you really draw? Where should you really start? Opposite side, and it really draws like this, but you have it. What do you think would happen if I did one small tweak and I did 6 sine theta plus 3? Plot the points. Ready? Plug in 0.